In this case, we're running a regression and we're trying to predict protein, the proportion of protein, but we're trying to do it not only from calcium, but also with calcium squared. In other words, these numbers squared. And it doesn't really matter if calcium squared makes sense or not in terms of in real life. I mean, you can square number of countries you visited, whatever it is. If it helps you with the explanatory power, it could be a plus. It does mean the interpretation of the model could be trickier, but this is a way to create more accurate models. So how do we get a calcium squared variable in here? Well, we click on add, and we are going to name this as calcium squared. And then we just hit calcium times calcium. And I'm not quite sure how there we go. Oh, looks like we did it. So if you look at 10 squared, negative 10 squared, you should get about a little over 100 there with the decimal included. So we're going to click out of that. And now we can run our regression. In Excel, by the way, you could have just made a formula equals this times itself and then copy that formula down. That would also work. So we're trying to predict the protein, holding down Control to select both of those, entering them both as covariates. And here we have our model. Let's take a peek at this. Notice, by the way, you can click on these little arrows depending on what portion you want to see of the data set or output. Okay, and then we look here at our regression equation. So we have the predicted protein proportion equals 0.48 minus 2.53 times the calcium variable minus 0.028 times the calcium squared variable. That would be our regression model. For part B, I'm going to switch back to Excel. I have a little more familiarity here with the plotting, and let me just get this calcium squared variable here too. So again, we could have done this in Excel versus JASP. That should be the same numbers, and that gives us that new variable here. But what I believe question or part B is asking us to do is to create a scatter plot here. And the assumption is we're going to see somewhat of a quadratic curve here. So we're going to fit a quadratic instead of the normal linear line of best fit. So we get this and click on some points, left click, right click, add our trend line. And the default will be linear, but then we can just change that to polynomial. Polynomial order 2 is a quadratic. And we could add axes, labels, and such. Also, the fit here is decent. It's certainly better than a linear, which linear would look like that. And if you looked at a residual plot, all these are under the line, these are all above. That's clearly a pattern going on that's not random above and below the line. So this, we still have a whole bunch of points above the line at once. It's not looking ideal, but it does look like a better fit than the linear. So having that quadratic in the model makes sense. Okay, for part C on the assumptions, I'm going to switch back to JASP and then grab a plot here, residuals versus, that's not what I wanted. I wanted the residuals versus the covariates. And here we really don't see a good pattern here. We see a bunch of points down here, a bunch of points up here, a bunch of points. It's certainly not randomly scattered above and below. In terms of the variance spread out across the x, that looks reasonably okay. The variance on the y is again not constant or anywhere near constant. So to be fair, we're really not meeting the assumptions well here. feels like we should do a bit more with this model. And I believe one thing we could try would be to add a cubic, but we're not going to do that right now. For part D, we're looking at whether the quadratic term was really useful. Again, I'm going to focus in on the regression model here. So here we have our calcium term, that's the linear term, and calcium squared, which is our quadratic term. We can see how the test worked out. It certainly was significant. This quadratic term was significant. So it does give us something above and beyond what calcium alone in the model would give us. And that t-test there, you can see our t-statistic of testing the null hypothesis that the slope of this would be 0. The t is strong enough to reject that null and say that the slope of this probably is not 0, that it is providing valuable information. And finally, the coefficient of multiple determination is going to be this r squared up here, 0.894, which we can convert to a percent, 89.4%. The interpretation of that is that 89.4% of the variance in these protein proportion, this variable that we're trying to predict, 89.4% of the variance in that variable can be predicted by knowing the calcium and calcium squared values.